Well, now we're going to start the 7th lecture, radar cross-section. And you'll note that I have it divided into a part 1 and a part 2. They'll appear all as one lecture, but there's a large number of view graphs. There's about 50 view graphs in the first part and 50 in the second part. But it will seem to you as though it's all one lecture when you look at it. First, a couple of comments. The field of radar cross-section calculation and understanding is a very complicated one. Everyone who reads the newspapers and journals knows about the low observable technology, the B2, the F-117. I'm not going to get anything near those things. They're far too sensitive and not necessary to understanding at all basic radar cross-section course. There are sections in the book that I use and is referenced in the sections. It's by Eugene Knott and John Schaefer. It's the second edition that Mr. Knott and Michael Tully is the third author. It's called Radar Cross-Section. And this second edition has a chapter on low observables, cross-section type stuff. You can read it at your leisure. And also, there's a very interesting book by one of the designers of the F-117 that you can buy on Amazon.com. Just Google Amazon F-117 and you can find it if you're interested in those things at an unclassified level. I'm certainly not going to go over any of that in this lecture. But I am going to go over in detail about radar cross-sections. Okay. Now, what are we going to talk about today? We're going to talk about the characteristics of the target. The relative, what I would say almost is the area that the electromagnetic wave sees is a metaphorical way of saying it. We're going to talk about this. Let's move on to the next view graph. How is the radar cross-section exactly defined? We usually denote it, first of all, in the radar equation in our calculations as sigma. And what we see here in this cartoon is a transmitter, and it's sending out an electromagnetic wave. There's a target here, and the incident electric field is the field right here near the transmitter. And the target, most of it is metallic material, conducting material, and Maxwell's equations have to be met when the electromagnetic wave impinges on this material, which is a conductor, and when it impinges on a conductor, it's going to induce currents, which will induce electromagnetic fields, and that's the causative reason for a scattered electromagnetic field in all different directions, which we call E sub s, from the target. And the cross-section, the RCS, is in the limit as we go to the far field, r going to infinity, of 4 pi r squared times the magnitude of the scattered electric field in the direction you're interested in measuring the cross-section, divided by the incident electric field, its magnitude quantity squared. So it's the hypothetical area that would intercept an incident power at the target, which if scattered isotropically would produce the same echo at the radar as the target. And that's the exact definition of it. So if you want to calculate, you know your incident field. If you want to calculate the radar cross-section, you need to know the scattered electric field. And that involves understanding Maxwell's equations very carefully, and how the Maxwell's equations of a plane wave in the far field is what a microwave radar beam would be, is how that plane wave interacts with targets of different complexity. Now, there are a bunch of factors that go into determining this radar cross-section. The first have to do with the target, its size, its shape, the material it's made out of, and its orientation. In this we've got a visualization of a cruise missile. If the cruise missile was made of all metal and the beam was hitting it sideways, there'd be a or any target hitting sideways, there'd be a big scatter off of that long parallel body that you'd see, broadside scattering. The material. You can have a perfect conductor, or there may be other materials that aren't so perfect conductors, that have conductivity, that are insulators, absorptive materials. Its size and shape. Is the target in the near field of the radar? If a missile has a radar seeker in it and it's heading towards the target, is the target in the near field of the radar on the seeker? The polarization of the radar emitting the wave, its frequency, because different pieces of the target, if it's complex, are going to be resonant or in the Rayleigh region or the optical region. Long wave relative to the size of the scatterer, or small relative to the size of the scatterer. Or you could have a bistatic radar where you send out a transmitting pulse and it doesn't come back, which would to the same antenna, which would be a monostatic mode, but a bistatic mode where another antenna at a oblique angle was receiving the scattered energy, and that's called the bistatic case. So we've got a whole bunch of different factors that go into determining the radar cross-section. Now, I say here the threats view of the radar equation. Now, obviously thinking in the military terms. And let's just say you're the view of the person who's in the seat of this plane and it wants to attack this ship. You're the threat in blue. Now, from your point of view, you can't control the power, the gain, and the wavelength of the radar on the ship, and you can't control how far away you are. You've got to go where you got to go, and these other terms are all parts of the radar. What you can control is the cross-section. So what obviously one wants to do is to have the target as small as the RCS as small as possible if you are a threat. And of course the transmitted pulse would go out, hit the target, and come back to the receiver in the radar. And of course the gains and powers connected in blue there, they're a part of the radar. Now, first thing we're going to do, that's the overview. The first part we're going to do is we're going to look at the radar cross-section of typical targets and how they vary with frequency, type of target, and that sort of thing. And that's going to give you a feel for the size of things. Then we're going to take a physical look at the scattering mechanisms and the contributors to the RCS of a target. And then we're going to say, knowing these variations which we see, and I'll show you a large number of examples, and the scattering mechanisms we're talking about, how do you actually go about predicting a target's radar cross-section? And the first thing we're going to do is we're going to look at measurements, how you'd go about measuring if you had the target or a model of it, how you'd measure its cross-section. And then we're going to be spending a very large amount of time how you could theoretically calculate now this cross-section. And the issue of theoretically calculating cross-sections is if you just go to Google Scholar and put radar cross-section in and look at the number of hits, you're going to get up into the thousands. This book by Gene Knott and colleagues is just one book, and it's got 500 pages. And by the way, Gene wrote the chapter in Merrill Skolnick's Radar Handbook, at least in the last two in that book. And so it's a shorter version of this, about 50 pages. But it's in a nutshell and a lot more contained. It goes over, and I'm not even going to go over radar cross-section to the depth that it's in the section in Merrill Skolnick's Handbook, because this is a very complex topic. Very complex topic we're going to talk about, and this is a subset. This is just to get you going. Okay, so let's first look at radar cross-section of different targets. I've just picked some numbers at random and how they vary with frequency and type of target and the like. The first one is an artillery shell. And if you didn't know, it's well known that different countries have radars that will detect artillery shells and where they're coming from, so that you can put counter battery fire, backtrack and put counter battery fire. And here we see a photograph, an M107 shell for 155 millimeter howitzer. So that's about 7 inches in diameter, and it's got a cone shape and then a parallel shape. Got like, a minus 23 dB cross section, smaller than 1/100th of a meter square nose on. And this is just a vanilla artillery shell, and it's in the 40 degrees of aspect angle off the nose. It's down in that region of minus 25 dB. Of course, when you go broadside, it goes up to minus 5 dB. And in the back, it's up in the minus 5 dB region. Here it's probably minus 2 dB. But the part you're going to be looking at, if the shell is coming at you at a slight angle, is this area. So that's a darn small cross section. Okay? And notice now I want to let you know where I got this data. Bill Fishbein has spent a long career working on counter battery radars for the Army, and he was awarded by the IEEE its Pioneer Award for his work in that field. And it's typical at that, when you're given that award, it's a very prestigious award, that you give an unclassified talk at the symposium that it's given at on what your history of working with the radar is. And that work you transform into an unclassified paper that is in the published in the Transactions of the Aerospace and Electronic System Society in one of their issues. And when I saw this, I hadn't seen an RCS versus aspect angle of an artillery shell, and I thought it might be a great example of a relatively low cross-section object. As we'll see, this is relatively low. As you'll see, this is relatively low. Now, I called Bill up on the phone because it didn't say anything where it was from or whatever, and in fact, I asked him what frequency it was. He didn't know, and it wasn't in the paper, so I have no idea what frequency this is at. And also, that he didn't know whether it was calculated or measured, and neither do I. But clearly, it went through release review, and this is the cross-section of an artillery shell at some microwave frequency, I would led to believe. Okay, now here we go to another class of targets, single-engine Cessnas. And here's a Cessna 150L at takeoff. You can see just one human being, relatively small. And here is in flight, that object. Gives you a good idea of the different scatterers. It's got rubber tires, wing, and just look at, this was measurements made at S-band, 10 centimeters, vertical polarization and transmit, vertical polarization and receive. And you see roughly, if you wanted to have a good chance of detecting this target, it's 0 dBSM. It's got a bump at 90 degrees where you're broadside, and another bump at 270 degrees, the other side, in aspect angle. And notice the fluctuations. We have in the artillery shell, notice there were few scatterers. It was relatively smooth. And here we have an aircraft that's got these struts to give structural strength to the wings that are above the pilot, and it's got some bars going out to hold the landing gear, and it's just what an aircraft would look like. It was a single engine aircraft, and it's fluctuating up and down. Okay, now let's look at an example And this was re-rendered by MIT's OpenCourseware, but it's taken from Dave Barton's Radar Systems Analysis book. And it's of a relatively simple object, a cone, cylindrical symmetry, with a sphere on the other end. And you can see in lines, this is the cross-section as a function of aspect angle. We've got very low values in the front forward aspect of near 10 to the minus 3. Peak value out at broadside here of 100 meters squared. And in the rear aspect, about 0.75 meters. And here we have these arrows point to calibration marks that were in the figure. And this is the reflectivity, the RCS. Now, radar A in a monostatic mode would see 10 to the minus 3 meters squared. But radar B, looking at the same object, would see 0.75 meters, even if it wasn't looking at the peak, if it was looking anywhere near the rear. So you can see that even relatively simple shapes, all kinds of different things you can end up seeing, and this shows significant change in cross-section of 50 dB between the forward aspect and the peak broadside. Remarkable, isn't it? So there's going to be a lot of differences. This shows very much the aspect angle dependence, but it's relatively smooth, and it's a smooth object. We saw a lot of fluctuations with the Cessna, and the size of the cross-section of about 1 meter square. And then when we saw the artillery shell and the nose-on aspect that you'd expect to be looking at it, if it was coming at you and you wanted to see it, well, minus 20 dB. So there's a lot of physical sense you can get from just looking at these three different view graphs. Now let's look at examples of different radar cross-sections, and this is adapted from Merrill Skolnick's Introduction to Radar Systems. Conventional winged missile is 0.1 meters squared. Small single-engine aircraft, as I mentioned, or a jet fighter, 1 meter square. And then we can go up to jumbo jets of 100 meters squared, helicopter 3, a large fighter 6, a medium jetliner 40. Then we have boats. A 5,000-ton displacement ship at L-band is 10,000 meters squared. A 40 or 50-foot cabin cruiser is 10. A small open boat, 0.02. An automobile, a small truck, 200. A bicycle, 2. A man, 1 meter squared. And then we go to birds. Large to medium birds, 10 to the minus 2 to 10 to the minus 3. And locusts and flies, 10 to the minus 4 to 10 to the minus 5. And I say that because that's an individual bird. And when birds are migrating, we'll show you later, when we talk about clutter, they can give very large apparent targets. So if you were an artillery shell was coming at you and it was flying through a flock of migrating birds, just the size, you won't discriminate the artillery shell from a medium to large bird just based on the size of the target. And notice the span is over at least 50 dB. At least over 50 dB. Now let's go to the second area, the physical scattering mechanisms and contributions to the RCS of a target. Okay, here we have, just as a generic target, a cruise missile, and it can have a lot of different things can contribute. There can be structural things like the shape of the body in blue, control surfaces that allow the the aircraft or the air-breathing vehicle to maneuver, the control surfaces, the wings. Then we've got the avionics. It can have a seeker within a dielectric nose, which will reflect through the dielectric in and out. You've got antennas, GPS antennas that could see up to know its location, altimeters to know its altitude off the ground, and then propulsion issues. We've got the inlets and the exhausts. They're all obvious physical contributors to the RCS of just about any object. And if this weren't a jet, you'd have propellers, turboprops. So you've got that whole issue of these physical entities that every air-breathing vehicle or object in the air. Let's look at the scattering mechanisms of an arbitrary target. The scattering mechanisms are a lot different than what the object is. And here I put a heavily laden fighter aircraft, and I want to point out from an electromagnetic point of view, when a wave hits this object, the different kinds of scattering mechanisms that are going to take place. We're going to have tip diffraction at the nose of the aircraft. We're going to have backscatter from a creeping wave that will go around. If the wave is coming in, the plane wave is coming into the side of the aircraft, it'll come in and it will creep around this conical section. At the surface between what would probably be the front part of the aircraft, which would hold an airborne radar, and the main body, a discontinuity. And that discontinuity at this edge will give you a discontinuity return. We can have a wave echo from a traveling wave that goes down the aircraft and hits a scatterer on the edge and comes back. We can have a return from the engine cavity, tip diffraction from fuel tanks or bombs, edge diffraction off both the forward and the rear edges of the wings, multiple reflections where the beam would come in and hit the aircraft, come out, and travel along the wing and go up, back, and seam, gap, and echo discontinuities, diffraction effects at the corner and the rear, and specular surface reflections off the side of this elevator. So for an arbitrary target, the scattering mechanisms are large, and they all have to be taken into account in any of the work we're doing. Now, here's the measured RCS of a C-29 aircraft model. The RCS as a function of the aspect angle. And I'm using, and here's a photograph of it. The C-29 this is just an Air Force version of a British Aerospace Hawker 125-100. And well, this data is from a 1/12 scale model measurement. And it's equivalent to X-band with linear horizontal polarization on transmit and receive, and a waterline cut, which means just at the horizontal. No aspect, no roll at all. And we see here the specula from the fuselage, the leading edge of the wing, and from the different places on the aircraft, you can point out, when you get down to it, the different physical effects will come at different aspect angles. Okay, now on to measurement.